Hello, welcome back to this course on structure, stereochemistry and reactivity of organic molecules and intermediates, a problem solving approach. Okay, we have seen that the different methods of generation of radicals, the tin method, the mercury method, the boron method, thiohydroxamic acid method. Okay. We have discussed so far the tin method and the mercury method. We will quickly finish up the other two. Okay. The boron method, interestingly that here you are generating a radical which is adding to bonds other than the carbon-carbon double bond. Okay. Here we have depicted this enone, and this X is a heteroatom, and then it is attached to an allylic imine bond. Okay. Allylic imine bond, and interestingly, if it is done in an intramolecular fashion, then the radical that will be generated with the help of a boron reagent that can add to this imine. So, now we are seeing for the first time the addition of a radical to an imine double bond, that is possible, and also now imine bonds, double bonds are weaker than the carbonyl bond. So, there is a possibility that the radical can add to the imine. The other is the radical can add to also oxime double bonds. Okay. Oxime, like double bond N O benzyl, that means benzylated oxime, that is also possible. Here the additional factor is that after addition of a radical at this center, you get a nitrogen radical, and then which is adjacent to a donor atom which is oxygen radical. So, there can be resonance stabilization by the oxygen lone pair, and then stabilizing the nitrogen radical. Okay. Because you know that one of the resonating structure will be nitrogen, nitrogen will have both the electrons, and the oxygen will sacrifice one electron. So, oxygen becomes dot plus and nitrogen becomes negative. Okay. Otherwise, the nitrogen will be occupying only single electron and the oxygen has the 2 electrons. So, this type of resonance can happen between in an oxime. Okay. So, that is why the radicals, the bottom line is that radicals can add especially in an intramolecular fashion to the to double bond, imine double bond or to oxime double bond. Okay. So, there are two nice examples that if you have these enone systems like this coupled with an imine double bond and an oxime double bond, then what you can do utilizing the triethyl boron in presence of oxygen, what happens, the triethyl boron generates, I told you, it generates ethyl radical. So, now what will happen, the ethyl radical, here there is no Ri, because the example that I told you in the last lecture was then ethyl radical will react with Ri to generate another fresh radical which is R dot. Of course, there is a catch here, it will happen only if the R dot is more stable than the ethyl radical. Okay. But here there is no R dot. So, the ethyl radical will add to this double bond. See, between these two double bonds, the radical will prefer to add first to the carbon-carbon double bond, okay, because that is the weaker bond. Remember that. So, the ethyl radical will add to this double bond, enone double bond, and with the formation of a new radical. Okay. So, you have ethyl here, you have a radical there, and you have, this is the system that we are talking about, N, and then suppose this is R. Okay. In this case, it was O benzyl and oxime. So, you generate this center in presence of triethyl boron, and then this radical now is well positioned to do a 5-exo trigonal cyclization, and you will get ethyl double bond, and so you will get a gamma lactone and N R. Okay. Obviously, there is now stereochemistry involved here and there. You are generating 2 two stereogenic centers, and the reaction is driven by the stability of the system. The trans isomer is obtained in 41%, whereas the cis isomer is obtained in 14%. Okay. So, ultimately you will get this will be NH, this will be NHR, or so if it is benzyl, then that will be O benzyl. So, this is one example of the boron reagent that can be used to induce an intramolecular cyclization and involving an imine or involving the oxime double bond. Okay. And the important point to note here, as I told you, that the reaction starts by addition of the ethyl radical onto the more vulnerable or more radicophilic. See, we have not introduced this term. This is the basically the radicophile means something which is looking for radical. So, a double bond is a good radicophile. So, I can use this term that the R dot will add to the more radicophilic double bond, and that is the carbon carbon double bond and not the carbon nitrogen double bond. So, the reaction first starts by addition to the carbon more radicophilic moiety, that is the carbon carbon double bond. Okay. So, that is the one of the example where triethyl boron has been used. As I said, literature is flooded with examples of radical mediated chemistry, and but we are just touching the ocean, giving you just some basic concept about these radical reactions involving carbon carbon bond formation and their utility. Okay. The next reaction that is quite interesting, that was developed by that is what is the thiohydroxamate method. Okay. The thiohydroxamate, let me see here. Okay. The thiohydroxamic acid method, I told you, that is another way of generating the radicals, and there are a lot of applications of this thiohydroxamate. But the thiohydroxamate, as I told you, the basic skeleton is this. This is the basic skeleton of a thiohydroxamate. Now, in case of the exact thiohydroxamic acid that Sir Barton used was a pyridine based one. Okay. So, a 2-thio, the sulfur is at the carbon sulfur double bond is at the 2 position of the pyridine ring, and so this is the thiohydroxamic acid of the pyridine from the pyridine moiety. Okay. So, this is thiohydroxamic acid because you have the requisite skeleton here, C double bond is in OH. Okay. And so, what happens here that this molecule is, as the structure says, it's not aromatic because of the formation of the exocyclic carbon sulfur double bond. So, its tendency will be to so how do you do that? Okay. So, basically it will have a tendency to add a radical, any radical, say with a X dot. Okay. So, if a radical adds to this sulfur, then this can come inside. Okay. This electron can come inside and make it aromatic, but that needs that you have to break this nitrogen oxygen bond, that is required. Okay. But the chemistry of this thiohydroxamic acid basically lies in this, lies here, that is the driving force is the formation of the aromatic ring from this 2-thiopyridine moiety. Okay. So, let us see how it was done, because our original target is to make an alkyl radical. Okay, with the help of thiohydroxamic acid. So, what was done? First, Barton developed a method where he took a carboxylic acid. Now, instead of in case of tin it is Rx, okay. In case of the mercury compound it is R a double bond containing an alkene moiety. Okay. In case of boron you have again you have to have a double bond where the ethyl radical adds. Okay. In case of Barton's method utilizing thiohydroxamic acid to generate radicals, his starting material initially what he developed was a carboxylic acid. The thiohydroxamic acid, as he said that it is not aromatic, that what Barton used, and so the one of the driving force is the getting back the aromaticity, and that can happen by a radical process as is shown here. Now, the question is it is very difficult to cleave an NO bond unless there is a driving force, other driving force that is required. Okay. So, let us see how Barton solved that problem. Okay. And also remember the fact that our main motto was to generate a radical, an alkyl radical, and then subsequently do a reaction on that alkyl radical. Okay. So, Barton took RCO2H and reacted with this thiohydroxamic acid. This is just simple DCC based coupling, or you can take RCOCl also and then take this this thiohydroxamic acid, and what will happen that this will form the ester OCOR, hydroxamate ester. Okay. So, hydroxamic acid and the ester of hydroxamic acid. So, this is thiohydroxamate. So, this that will be formed from the carboxylic acid. Now, what will happen? This is not a very stable system. First of all, its intention to retain the aromaticity, that is, or regain the aromaticity, that is number one. And number two is that now this bond is very vulnerable, because you can generate carbon dioxide if you do an electron flow like this. Okay. So, in presence of light, what happens that in presence of light you get slight excess, slight decomposition of this, a tiny amount is decomposed in presence of light. Okay. So, that means you will generate an R dot. Okay. Now, in the medium, suppose I have a reagent like a reagent which can donate halogen atom like CBr CCl3, bromo trichloromethane, or you can take iodoform CHI3 which can deliver or which can donate iodine atom. Okay. Or you can take CBr4, that is also possible, which will donate one bromine atom. So, anyway, any halogen atom donor, if you give that, so what will happen? Now, R dot will form this RBr, if it is bromotrichloromethane, RBr plus CCl3 dot. Okay. Now, this CCl3 dot, like whatever I have shown here, will come back and add to this sulfur. This becomes aromatic. This cleaves in turn, because earlier the problem was the cleavage of the NO bond. This breaks in this fashion, release of carbon dioxide and formation of R dot. So, basically now you are having continuous generation of this R dot, and R dot is reacting with the bromotrichloroethane methane and then generating the trichloromethyl radical, okay, and that adds to the sulfur. So, there is a chain propagation, this is continuously being generated, and as it is generated you continuously generated the R dot, and the R dot will automatically react with bromotrichloromethane generating fresh trichloromethyl radical. So, the chain propagation happens. So, what is the product of this reaction finally? The RCO2H is ultimately converted into an important product which is RBr. Okay. Remember, there is a method where carboxylic acids can be converted to, can be decarboxylated to RBr, and that is called Hans-Dicker reaction. okay, but that requires silver, no, formation of the silver salt and bromine. But this is a method which is better. You actually do not handle bromine at all. Instead, you are utilizing brominating reagent, bromo reagents, not bromine itself, or you can take also iodine compounds which can deliver iodine atoms, and it happens in a much milder condition. Okay. Even amino acids, if you want to convert glutamic acid and do this decarboxylation, you protect the glutamic acid with suitable protecting group and then you do the reaction. So, the Barton decarboxylation method, and you get the Br. Remember, one thing we should remember, that if you do not use any brominating agent, but if you use a hydrogen donor instead, then what you will end up is basically RH. So, that is nothing but a decarboxylation of a carboxylic acid. Okay. And you know, decarboxylation of carboxylic acids require harsh conditions, soda lime and then heat. But in this process, if you take a hydrogen donor instead of this bromine donor, then your ultimate product will be RH. But this is happening only at room temperature. Okay. And so, that is the beauty of the reaction. The other point is that the byproduct of this reaction is CCl3 is a basic compound. Okay. So, you can always wash this out using an aqueous acid. So, pyridine compounds will be washed out. Okay. So, workup is easy and the yields are high and the reaction takes place very mild condition. You see the temperature 20 degrees centigrade, tungsten light, and then you can use various halogen atom transfer reagents. Okay. So, that is what is Barton decarboxylation method. Okay. Then Barton did one more extension of this method, and that is, suppose if you do not have all the time, if you do not have the carboxylic acid to generate the R dot. Okay. So, some people thought that it could be a limitation. So, whether this method is useful in formation of R dot from ROH, whether that can be possible, because earlier the method was RCO2H giving you R dot. Okay. So, in order to do that, it is a clever trick employed by Sir Barton, that is, so he first made the half ester of oxalyl chloride. So, if you take oxalyl chloride, that means COCl and add half equivalent of this thiohydroxamic acid. So, what you will get in presence of a base, you will get the half ester, and then once you have the half ester, now you add your alcohol, you add the alcohol part from where you want to generate the R dot. So, that will form OCO, then CO and then OR. Okay. Now, again you see, in presence of light, this is the vulnerable bond, because you can generate carbon dioxide. Okay. In fact, you can generate 2 molecules of carbon dioxide that will come out, and then you have basically with this decomposition process you have generated your desired R dot, but that what you need in a tiny amount, because then if you have your whatever hydrogen atom donor reagent you have HX. So, that could be a thiol. So, R dot will take the hydrogen and generate the X dot, which will carry the chain forward. Okay. So, X dot again will now add to the sulfur, this becomes aromatic, and this type of breakage will continuously take place, and so it is a chain, it is a chain propagation. The propagator is basically the X dot which is continuously being generated. So, you see you can generate R dot from RCO2H, then you have to form the directly form the ester with this hydroxamic acid. If you want to generate R dot from alcohol, then you have to use the half ester. Okay, you use oxalyl chloride. So, half of the thiohydroxamate is tied to one part of the oxalic acid and the other oxalic acid part is tied up to the alcohol, and then by shining light you can generate the R dot in presence of a hydrogen donor, which is usually a thiol. Okay. So, that is the Barton reaction. So, we have covered all these 4 methods that are usually employed to generate radicals, and there are useful radical reactions that we have discussed. Okay. Now, just one more thing I want to tell you, that there are earlier I have in the beginning I told you that radicals are very short lived species, which is true, and they are only generated in situ during the course of a reaction. However, there are some molecules which are stable radicals and which can be stored in a bottle, and they can be purchased, they can be utilized. So, they are quite stable, and one of the compound is what is called tempo. Tetramethyl pyridine N oxide radical. Okay. Tetramethyl pyridine N oxide radical. Now, this is very stable radical because of the presence of these 4 methyl groups, which are acting as a steric shield to protect this radical. This radical cannot be quenched because other molecules, it is difficult for the other molecules which are hydrogen atom donors or those type of species, difficult to approach and quench this radical. So, that is one of the reason that why this tempo or the N oxide radicals are very stable. Many of the N oxide radicals are quite stable, and one very common reagent is this tempo. Okay. I forgot to mention another point when I was talking about detection of radicals in a reaction. Sometimes what happens that you do the reaction in presence of tempo, okay. And if a radical is generated in situ, then what will happen, that can be quenched by tempo, and you will see a gradual reduction of the EPR lines in presence of the tempo. So, this tempo based experiments in EPR is also done, or sometimes the reaction is inhibited in the presence of tempo, because as like oxygen which inhibits radical reactions, similarly other radical species like tempo can inhibit the rate of the rate of a radical reaction. Okay. There is one example where tempo has been utilized as an oxidizing agent, that is quite interesting, tempo based oxidation. Okay. And I want to finish up the radical chemistry by showing this slide, that is the what is called tempo based radical tempo based oxidation of alcohols to aldehydes. Okay. What happens here? This is the tempo molecule. Okay. Big reagents cannot approach, it is difficult to approach this oxygen radical. However, what you can do electron transfer processes that can happening, because electrons after all will not does not require any space. Okay. So, what you do, if you can further oxidize this molecule, if you add an oxidizing agent like sodium hypochlorite, a bleach, common household bleach. Okay. If you add sodium hypochlorite, then what will happen? This there will be loss of one electron from the nitrogen, and so nitrogen will become 1 dot and oxygen 1 dot, and that will form this N double bond O, but the nitrogen will be positively charged because it has lost 1 electron. So, that is oxidation. So, you can remove 1 electron from the nitrogen, and the result is that formation of this nitrosonium ion. Okay. And so, you have to use an oxidizing agent, and that oxidizing agent is very often is sodium hypochlorite. Okay. And now, this is a new oxidizing agent that you have generated. Okay. So, in presence of say a primary alcohol RCH2OH, the alcohol now, let me write here N double bond O plus, and these are the tetramethyl groups, and now you have RCH2OH. So, now the now what will happen, this will be, you cannot actually write this type of okay, this is okay. So, it attacks the nitrogen with the result that it is the NO bond is broken, okay, and that will form an intermediate. See, when you use a tetravalent nitrogen, you have to break the other bond at the same time, because pentavalent nitrogen is not possible. So, that is why what I was doing is, at the same time you are attacking the nitrogen and you are breaking the NO bond. Okay. So, that will form in O minus, okay, and this will be OCH, because this is CH2 and that is R. Okay. So, this intermediate is formed. Now, there will be an intramolecular hydrogen transfer, because the N oxide will abstract the hydrogen. See, ultimately you want to do the oxidation of the alcohol to the aldehyde. So, it has to lose hydrogen, and this is how it is doing, that first oxidation of the tempo. So, tempo you add in minute amount, okay, and then you add an oxidizing agent. Tempo is oxidized to this nitrosonium ion, the alcohol adds to the nitrosonium ion, and then very similar to what happens to a carbonyl, that the nucleophile attacks the carbonyl. Here it is nitrogen, the electrophilic center is the nitrogen, and you form this intermediate, and the oxygen now abstracts the hydrogen in an intramolecular fashion. This goes here, and that comes back. The nitrogen is still, remember, nitrogen is still plus, because nitrogen has lost the has not gained anything. It has lost 2 electrons, and it has gained the 2 electrons from the alcohol. So, basically it remained positively charged, and that goes there, and this comes here. So, what it makes? It makes, first of all, this goes at as aldehyde RCHO, that what you wanted, the oxidation product of the alcohol. And what about the species from the tempo? So, that becomes the, this is the tetramethyl, and now you have N, and this will be OH. So, N hydroxy compound. Okay. This is not tempo, but you have used one equivalent of sodium hypochlorite. So, now sodium hypochlorite will start oxidizing it. First, it removes the hydrogen to form the tempo. So, this N oxide radical, and then that is further oxidized to the nitroso compound, nitrosonium ion. Okay. So, that is the method. It basically recycles. Okay. So, this is, you need excess of sodium hypochlorite, because you have to do oxidation twice. One is this N hydroxy back to tempo, and then tempo to the nitrosonium ion. Okay. So, you have to use excess of this oxidizing agent and a tiny amount of tempo, but this is a very mild way of doing oxidation of alcohol to the aldehydes. Okay. There are many methods of oxidation of alcohol to aldehydes. The famous ones are the chromium based methods, but they are quite harsh methods. Okay. Earlier it was chromic acid, then it was modified to PCC, then PDC, and then there are reagents called Swan oxidation, there are this Des-Martin par iodination, but this is another method, a tempo based oxidation, which is which uses a co-oxidant, and that is this usually the sodium hypochlorite. Okay. So, you see the breadth of the radical chemistry. The radical chemistry, it started all from the from your formation, the formation generation, how you can generate radicals, and then where it can be useful. If you talk about the parabenzynes where diradicals were generated, radicals are very useful materials from the standpoint of biology, because they are the intermediates for showing anti-cancer activity. They are the intermediates for making carbon-carbon bonds. They are the intermediates for making polymers, that how the radical chemistry generated, and they are the intermediates for generating for decarboxylation, for dehydroxylation like ROH to RH, and for formation of various skeletons, interesting skeletons which are important from biological standpoint. And finally, what we have done, the use of a radical based material, a tempo to oxidize for a mild oxidation of an alcohol to an aldehyde. I think with this we come to the end of the radical chemistry, and from so we have actually orchestrated, we have arranged this course in such a way that initially we had we had discussed the structure of a molecule, because our initial lectures were mainly on stereochemistry, then the how to describe the stereochemistry of a molecule in terms of the symmetry elements. Then we did the conformational analysis of several bicyclic, polycyclic compounds. Then we went for one important aspect that controls the reactivity of molecules, and that controls how a reaction can go, which pathway it will take, that is namely the stereoelectronic effects in organic chemistry. Then the Baldwin cyclization rules that we have done, and then we came on to some of the real life molecules like the arines, the alkynes, the allenes, the ketenes, and now the radicals. So, we have done all these. So, next day we will now talk about some other functionality which can generate which are also very useful for carbon-carbon bond forming reactions, and we will discuss the stereochemistry of those reactions. Our specific target will be the addition reaction onto carbonyl compounds. Okay. So, till then, goodbye today. Thank you very much.